Now we begin looking at division. Just like all the other arithmetic we have looked at, we want to start by doing an example by hand to kind of remind ourselves of the steps and the terminology. Okay? So if you look at this right here, I'm going to copy this. I'm going to do this division by hand using long division, and I'll follow along with this example. I'm going to take 15 decimal divided by 7. And the first thing is, what are the names of the terms? Okay? First of all, the bottom one is called the dividend. Dividend. Okay? This number out here is going to be the divisor. And this is like saying 7 divided by 15 in fractional form. Okay? So you put it in long division like this. Okay? When you perform this in a computer using fixed point, you are always going to have a result which gives you the actual quotient and a remainder. Okay? So we're never going to do anything weird. We are always just going to have a result which is the quotient and the remainder. I begin reminding myself how to do long division, and what ends up happening? I say, does 7 go into 1? The answer is no. So I record it up here. Then I move along to the next position. But in reality, what I actually did was I said, I'm going to multiply 0 times 7, bring it down here, then I'll subtract, I'll bring on another position, and I'll go 1 minus 0 is 1, then I'll bring down this position, so I've got 15, and I'm going to go, does 7 go into 15? The answer is yes. It goes in 2 times. Notice that I'm now done with my division, so then whatever's left is the remainder. So I continue to do it 2 times 7. I get a 14er. I subtract that. This now is my remainder. Okay? So that was the answer. So this right here is my quotient. This down here is my remainder. Now, we got the terminology taken care of. One of the subtle things, though, that we wanted to keep track of when we flip this over to binary is this notion. When I did my first step, I said, does 7 go into 1? I treated the first bit of my dividend as having the same weight. I didn't do this. I didn't do, does 7 go into 10? I did, does 7 go into 1? So I treated this as if it was in the same position. Even though when I look at this number, this has 2 positions. This is going to have a higher weighting than this that only has 1 position, but I treated that as if it was in the same position. That becomes important when you build a binary circuit to do this, because we have to do that in our circuit. So now let's take a look at how this might look if I did binary division. Okay, here we go. I'm going to do the following. I'm going to just give you the number of bits that will ever exist in the quotient and also in the remainder. It turns out that if I took a dividend that had 3 bits, A3, A2, A1, and A0, and I divided it by a divisor that had, 4 bits, so this is n is equal to 4. This is going to be B3, B2, B1, and B0. I'm going to have a quotient that is actually 4 bits. I can have a quotient 3, quotient 4, quotient 2, quotient 1, quotient 0. If I wanted to test that, to prove that that's true, I could look at the corner cases of the numbers that can be represented with 4 bits. When I test it, I immediately will reveal another complexity of division. If I wanted to test this, I would say, what are the biggest numbers that I can take on? Well, biggest and smallest for that matter. I can take on a 0 is the smallest, and I can go up to a 15. So the interesting conditions are when I do something like this. If I do, how many times does 0 go in to 15? That's a test. What's the answer? Undefined. It's undefined. Okay? It's undefined. This is a circuit that you have to actually build that is going to override the result. This is the only arithmetic that actually has an invalid input flag. So whenever you have a divider circuit in any sort of system, it is going to check to see if the divisor is a 0, and it will flag it and say, invalid. I'm not even going to do this. So what you do is you usually set a flag or you put some weird code that says, I can't go on. Okay? So this is a separate circuit. So we don't actually look at that when we build the circuit itself. We know a separate circuit will exist, which will say undefined, friend. Okay. Now, what about the other condition, which would be, okay, how about 15 goes into 15? That's 1. That's stupid. We can represent that. How about the other condition where we go 15 goes into 0? What is that answer? It's actually 0. What would be the remainder in that situation? It'd be remainder of 15. Ooh, is that the largest remainder you would ever have for these conditions? It actually would be. There's no quotient. The remainder is 15. We have immediately proven to ourselves that the largest remainder would be how many bits? 4 bits. So we'd actually have a remainder which is 4 bits. We haven't proved ourselves what the quotient's going to be yet, but we did figure out that this remainder is 4 bits. Let's look at some other cases. Since we can't divide by 0, or we can't have 0 on the top, we could have its next smallest number, which would be what? 1. So a test case might be, since this was invalid, we could actually have 1 goes into 15, and the answer there would be what? It would be 15 with a remainder of what? 0. Is this the highest quotient we could ever possibly have? The answer is yes. You know it's the highest quotient because you don't have a remainder. So this means that I could represent 15 with 4 bits, and that indeed is what we have on the quotient. The quotient will be 4 bits. Now, if you perform 4-bit division using fixed point numbers, you will only ever have a 4-bit quotient and a 4-bit remainder. You actually need 8 bits, but you do it as 2 actual answers. You have a 4-bit quotient, 4-bit remainder. All right. Let us do a example by hand, which will show us how you could potentially do binary division. I'm going to do this. I'm going to take 2 example numbers. I'm going to take 1, 1, 1, 1 divided by 0, 1, 1, 1. Okay? The answer to this is what? Let's go over here and just put the answer. Really what I'm doing is, how many times does 7 go into 15? The answer is 2 remainder 1. So let's now work through this and see what happens. I am going to start by doing this division of, does this number go into this number? You know what you immediately have to do? You got to remember, you treat this number as if it's in the same position or has the same weight as this. So this right here is actually, what you're trying to do is say, does 0, 1, 1, 1 go into 0, 0, 0, 1? See how this was treated as if it was the least significant position. So I had to pad 3 zeros onto it. Okay? So the answer to this is actually no, and I could tell that by looking at the decimal numbers. Does 7 go into 1? No. So I say no, it does not. I'm going to go 0 times this, and what do I end up getting? I get a 0. But what's really fascinating about it is that I take that 0, and I assume that these bits are still there. So I almost have like these invisible bits that are sitting right here that are part of the dividend. So then I say, okay, well, I'm doing this position. This puppy's coming down as just a 0. So now I'm going to do 1 minus 0 is 0. Let's bring the next one down, and I get an A. That's not even close. This is 1, and I bring this guy down, and it's going to be 1. And now I'm ready to say, okay, does 0, 1, 1, 1 go into 1, 1? Remember now, though, I got to treat it in the right position. So this now becomes as if I'm asking, does 0, 1, 1, 1 go into 0, 0, 1, 1? The answer is, does 7 go into 3? It's actually no, that's not true. So it's like, okay, it's a 0. So now I go 0 times this. I bring this down as 0, 0. Remember, I'm treating these as if now they have 2 leading bits, and I'm keeping their position straight. So now let's go down to the next one. And I say, okay, what's 1, 1 minus 0, 0? It's going to be 1, 1. I bring this fella down. It's going to be 1. And now I get to say, does 0, 1, 1, 1 go into 1, 1, 1? To see it more clearly, I just remember I have this leading bit out here because I'm keeping track of the positions. The answer is, does it go in there? Yes, it does. So does 7 go into 7? Absolutely. I take 1, multiply it by this. I get myself a 0, 1, 1, 1. I subtract that, and what do I get? I get 0, 0, 0. I bring this down, and now I'm finally in my last position where all the positions match, and I say, does 0, 1, 1, 1 go into 0, 0, 0, 1? Does 7 go into 1? The answer is no, 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 no. It does not. I multiply this over. Now it's in the right position. I perform my final subtraction. I know it's the final subtraction because I'm in the leasing of a bit. The answer is 1. This is now my remainder. This is now my quotient. And the answer is not only correct, but what I would end up getting is I'd say 0, 0, 1, 0 with the remainder of 0, 0, 0, 1. This is now 8 bits. Okay, how did that feel? I don't know. That's a lot. It's kind of a lot. The question, you know, it was kind of straightforward, but you know what? The question that we kind of jumped over, I don't know if you noticed it, but does 7 go into 3? And what did we, when we looked at this, we were like, does 0, 1, 1, 1 go into 0, 0, 1, 1? What did we do as humans? We're like, I don't know. Flip that into decimal, and I'm going to use the memory that I've built with flashcards. So we said, does 7 go into 3? You're like, no, no, no. But how do you build a circuit that does that? The trick could potentially be this. What if I took 7, and I said, does it go in to 3? What if I subtracted them? Exactly. If I took 7 minus 3, I would get a positive number. That means it does not go in. But what if it was a bigger number like 7 minus 7? That's equal to 0. That didn't work. What if it was 7 minus 8? Does it go in? The answer is it's a negative number. It does go in. So we have a situation where you can perform subtraction to figure out if it goes in. Okay? This is actually how you perform division by building a combinational logic circuit. What you do is you build a circuit which is called an iterative subtraction circuit. The circuit on here is actually quite large. If you look at it, this is what the circuit looks like. Notice a couple different things about this. One thing is that the first thing you do is you pad up the number with zeros when you perform the first subtraction so that the first bit that you mess with is 4 bits wide. Okay? And then what you do is you say subtract those two. Then you're going to get a result, and what you're really caring about here is whether the sum bit or the sign bit was a 1 or a 0. If it was a 0, that means it didn't go in, and you can feed that puppy right on down to the quotient. Boom. If you then said, I want to take that number and bring it down, what you do is you route it through, and you start bringing this guy over. You bring this guy down to the next subtraction, but you wanted to either bring in the 3 bits from here, or you didn't want to bring them in. That's how you perform that multiplication step where you take this and multiply it over. So what happens is that you use multiplexers to bring down here, and that's how you get the next quotient. Then you bring down this guy. You use multiplexers to pad it down with the remaining 3 bits. You repeat that until you get your 4-bit quotient. And what will happen is that after you're finally done with those 4 bits, what's left on the final subtraction is the remainder. This is called an iterative subtraction method for performing binary division. Okay? It's pretty complicated. It's a pretty large circuit. Okay? Here is a trick though. Division even more so than multiplication, we can logically shift right to divide by 2. Okay? It's the exact same thing. If I had 0, 0, 1, 1, and that's equal to, no, that's a horrible example, 0, 1, 0, 0, and that's equal to what? 4. If I logically shifted right, 0, 1, 0, and I threw away this bit as it shifted out, and I padded with a 0, what is this number equal to? It's equal to 2. A logical shift right is a way that you could actually divide by 2. This is actually very powerful because you do a division by 2 quite a bit. When these logical shifts break down is when you run out of bits. You run out of accuracy. Because what happens when I divide again? All of a sudden you're left with 0 and you don't have any meaningful information. Same way if you were multiplying and you were shifting this way, as soon as that most significant bit starts falling off the left side, the multiplication's over. Okay, so that is how you perform binary division.